Hello, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinar units. And I again thank Dr. Kurz Larson and the NASA Engineering and Safety Center, NESC, for making this series of webinars possible. And today we're going to be discussing rainflow cycle counting for continuous beams. And we've been on the subject of rainfall cycle and fatigue for the last couple of webinar units, and we're actually going to spend about maybe 4 or 5 more on fatigue as well. And just as a review, I showed this slide in the previous webinar on rainflow counting, and this is a pagoda. It's on an island in Japan, and there were two Japanese engineers and researchers named Endo and Matsuishi. And they published a paper in 1968 where they developed the rainfall counting method by relating stress reversal cycles to streams of rainwater flowing down a pagoda. So you can see the different streams of water coming down the various roof sections there, and they intersect one another and drip down in a certain pattern. And this became the inspiration for Endo and Matsuishi's rainfall cycle counting method. And the method that I'm using is in the implementation of their method that I'm using is taken from ASTM E1049-85. So I encourage you to get a hold of that reference yourself. And anytime we do a fatigue analysis, well, at least for certain types of fatigue analyses, we need an SN curve. And the one I'm showing here, it's just for reference only, so please don't quote me on this, but it's for aluminum alloy 6061 T6, and this is assuming a stress concentration factor of 1 and a stress ratio of -1. That means that the stress is oscillating symmetrically about the zero baseline. And along the y-axis is the maximum stress, KSI, and this is a 0 to peak stress. And along the x-axis is cycles. And this curve, it can roughly be divided into two sections. Of course, it's in linear log format. But we have the first section here. It's somewhat flat due to strain hardening effects. And then there's a bit of a curved line here, but we can approximate that by a straight line. Okay, so this portion here is the low cycle fatigue portion. And then the high cycle fatigue portion is shown here. And some materials also have an endurance limit, but that's kind of vaguely defined or nebulous for aluminum. Okay, and as long as the maximum stress is below, let's just pick a number. As long as the maximum stress is below 40 KSI, what we can effectively do, just for simplicity, is represent this as just a single curve. Now we're going to be doing an example here, and this is going to be based on the Mill Standard 1540B ATP power spectral density and G square per hertz versus frequency in hertz. And we're going to be applying this as a base input, or more properly as a forced acceleration to a cantilever beam, where the beam is modeled as a continuous system. And we're going to have a duration of 3 minutes. So let's go ahead to our Matlab GUI package here. So let's type in vibration data. And this Psd that we're going to be using is now one of the library functions. So let's go to library array, Mill Standard 1540B, ATP Psd specification. We'll read that in. Okay, it's going to have 2 columns, frequency in hertz and G square per hertz. So you can see that array appears in our workplace there. In fact, I'm just going to kind of copy and paste that name. Copy it and paste it later. Let's go back to our vibration data, and we're going to synthesize a 180-second time history to match that Psd. So time history synthesis from white noise. And we've run this script, or this dialog, a number of times. Preloaded into Matlab is mil standard underscore 1540b. G units, G will do the English units there. 180 seconds, and we need to view the processing options. And we're going to choose row 10, and this is going to give us a delta F of about 2.8 hertz over 1,000 statistical degrees of freedom. So expect the Psd from the synthesized time history to be very smooth. Let's go ahead and run that calculation. We'll pause while we watch the progress bars scroll by. And a number of plots appear. But before we do anything else, I'm going to save this acceleration time history as synth, S-Y-N-T-H, before I forget, because we're going to be using that in an upcoming exercise. Okay, back to our synthesis. So here's our power spectral density. The blue line here is going to be the Psd of our synthesized time history. And then the nominal specification is the red line. And you can see that the Psd of our time history synthesis is well within the tolerance bands. And that really is coming about because we do have 180 second duration, and we've chosen a case that gives us over 1,000 statistical degrees of freedom. So that's why it turns out so well. Here is the histogram of the acceleration time history. Here's the displacement time history, and just notice that it oscillates symmetrically about the zero baseline. Similarly, the velocity time history also oscillating about the zero baseline. And then here's what we just saved. It's the acceleration time history, g's versus time in seconds. And it's not white noise, but it is broadband random. And it corresponds to a shaped power spectral density. So just zooming in several times, that's what we get. It's a broadband random vibration time history. Okay, the next thing we're going to do is figure out our beam parameters. So let's go back to our slides. So these slides here just reminds you how to call up that Psd function and how to synthesize the time history, which we've done many times before in this series of webinars. So save that as synth. Okay, there's the Psd, the slide version Psd. Now let's go to our continuous cantilever beam. So this beam is it's fixed free, but when we say fixed free, that's for the purpose of doing the normal modes calculation. And otherwise, this beam, we could say it's going to be subjected to a base input, but it's probably more proper to say we're going to apply a forced acceleration at the otherwise fixed node. So we've got material aluminum, 2 inches wide, 1/4 inch thick, 8 inches long, elastic modulus, area moment of inertia, mass per volume, mass per length. Viscous damping ratio 0.05 for all modes, or you could say 5%, or equivalently the amplification factor is Q is equal to 10 for all modes. So let's go to our beam calculation GUI dialog, and we must have run this before. Let's run it again. It's under structural dynamics, and let's go to beam bending, and we're going to do general beam bending. There's a couple other beam options as well, but let's do general beam bending. Let's perform analysis. Okay, so this script calculates the bending natural frequencies of a beam. Ours is fixed and then free. English units, and the numbers for our parameters are 8 inches long, rectangular cross-section. Thickness is 1/4 inch, width is 2. Aluminum, elastic modulus, and mass density are a part of the material library. Let's go ahead and calculate the natural frequencies, see what we get. So 124 Hertz for the fundamental mode, and then you can see the second, third, and fourth modes with the corresponding frequencies. We can also take a look at the mode shapes, and these are just normalized to have a peak amplitude of 1. As the fundamental mode, so you can see at the fixed end, there's no displacement, there's no rotation. And then we have the free end there. Here is the second mode, then the third mode, and the fourth mode. And we can also look here in the command window to get some further information. So we have the first 4 modes, the corresponding natural frequencies, and then the participation factors and effective modal mass values. And I've got a paper on my blog that can explain these participation factors and modal mass values better than I'm going to do now. But basically what I want you to know about participation factors is that these modes have different levels of excitability. And the most excitable mode is the fundamental mode. And then there's a diminishing effect that occurs as we go to higher and higher modal frequencies. So that means that and we'll see this, that for our the bending stress analysis, most of the stress is going to be tied up in the first mode. Okay, so what next? Let's apply a base excitation. And before we do that, we're going to have to specify the damping. Now you can either pick Q or viscous damping ratio for input. And we are going to have uniform. So I'm just going to type in Q is equal to 10. That's equivalent to 5% damping. Now we're going to save the damping. And we can go to our Matlab command window and we can see, okay, here's our first 4 natural frequencies. Each one has Q is equal to 10, and each one has 5% damping. So it's just good to double check and make sure everything's in order there. Now let's go to arbitrary pulse. We're going to apply a arbitrary pulse as a base input, or more properly as an enforced acceleration to that beam. So beam response to arbitrary base excitation. The input array must have 2 columns, time in seconds, and acceleration in g. So let's do all 4 modes, and the dialog already knows we have an 8-inch beam. The input array is synth. That's our synthesized time history. And for response, this will be the distance from the left boundary. We want to focus in on the bending stress at the fixed boundary. So I'm just going to type in 0, and that will correspond to the fixed boundary. Let's calculate. And a bunch of plots go by, but before I do anything else, I want to save this bending stress because we're going to be using it for some other part of this exercise. So it's bending stress, save. So now that's saved in the Matlab workspace. Okay, before we look at plots, let's just look at some numerical output here, the command window. So there's those first 4 modes again. And their participation factors, the damping ratios. And then this is just a summary of the peak values at each of 3 locations. So for absolute acceleration, you can see the peak values at the 0 point, that's the left boundary, at the intermediate point, 4 inches, and at the free end is 8 inches. So we have our 3 peak accelerations at those locations, and then similarly if we have peak relative velocities at the 3 locations. We have the peak relative displacements at each of 3 locations. Similarly for the bending moments. And a fixed free beam has the characteristic that at the free end, the bending moment should go to 0. And that's approximately the case there. Okay, distance from the neutral axis is 1/8 of an inch. And here's our bending stress. And this is our peak bending stress at the fixed boundary. And it's 2,790 psi. So kind of keep that number in mind. So now that we've done this, well, let's go back and check the size. We're gearing up to our Rainflow here. Okay, so those were the natural frequencies and participation factors and effective modal mass values. So we entered in our damping. Q is equal to 10. We applied our arbitrary excitation. We saved our bending stress. Now we get to go to Rainflow. So there's at least 2 different ways we can get to our Rainflow analysis. So if we go back to that, and sometimes I get things closed out before I meant to close them out. Okay, here we go. So one way is we can go to our Rainflow analysis via this button here. But if by chance we got out of that window, we could also go to the main GUI page and go time history, stress, rainfall cycle counting. So either way gets us to the same place, but let's just do it from this point here. Okay, we talked about this last week, but we probably ought to talk about it more again today. So this is rainfall cycle counting per ASTM E1049-85. The input array must have 2 columns, time in seconds, and acceleration. Note that the amplitude in the resulting table is going to be peak minus valley divided by 2. So we kind of need to be careful about terminology. So when I say amplitude, I'm referring to peak minus valley divided by 2. Or if I say range, that is simply peak minus valley. But that convention is not universal, so whatever you're dealing with, just make sure that you understand. Our input array is bending underscore stress, and it is stress in PSI units. So let's put stress in PSI units. Now we have to make a choice, and for the numerical engine, we can do the calculation directly in Matlab, and that can be very slow, however, because as part of that calculation we have to delete intermediate array elements, and Matlab can do that, but it does it in a fairly slow manner. The other thing we can do is a Matlab Mex implementation, and Mex requires a C++ compiler. It's faster, and there's some steps shown here that are just one-time setup steps. But let's go back to require a C++ compiler. Now, you may never have ever programmed in C++. You may have no interest. But if you want to do a good way to download a C++ compiler is go to code blocks. So let's just do a Google search on code blocks. And there's an official site for code blocks, and just for a quick download, you can go to the SourceForge site. And this is free. And code blocks is actually an IDE. It's an integrated development environment. But it also is bundled together with a C++ compiler, which is MingGW. So if you want to, this is just kind of a fairly quick and easy way to download your C++ compiler. And once you've done that, you don't even need to open up the IDE or do anything else. You would just need to go into your Matlab and do, just as a one-time, go to the Matlab prompt, say mex space _ setup, and this will allow Matlab to get connected up with your C++ compiler. And then also as a one-time step, you type in mex space rainflow _ mex.cpp, and that's the C C++ source code that's it comes in the vibration data zip file that has all the MATLAB scripts. And once you've done that and everything compiles successfully, then you never need to do any of these steps again. You can just go to Matlab Mex, and everything should have just happened seamlessly at that point. Let's go ahead and calculate our rainflow. We're going to do Matlab Mex. It'll take a little bit of time, but hopefully not too much. Okay, a couple things come up, a table, and I'm not really all that interested in this table, so I'm going to click out of it. I'm really not interested in that plot either. And here was our bending stress time history at the fixed boundary point. And by the way, I should have mentioned, everything we're doing so far is stress concentration factor of 1. We're actually going to go back in and do higher stress concentration factors as a follow-on exercise. But for right now, we're in stress concentration factor equal to 1. So you might say, well, that was kind of anticlimactic. You just clicked out of the table and figures. But here's what we really want to do here. We want to save the rainflow amplitudes in cycles. And we talked about these last week, so I'll just say amp underscore CYC. This is a file that has 2 columns. The first column is going to be the stress amplitude in PSI. The second column is going to be cycles. And the cycles are binary in the sense that they must be equal to either 0.5 or 1. So let's go ahead and save that. Okay, that's now in our MATLAB workspace. Now we're going to do a miner's cumulative damage. So this is valid for stress time history. So let's calculate. So this script calculates the palm grid miner cumulative damage index. The rainflow, stress amplitude, and cycles array must be the input to this script. So amp underscore cycles, and PSI is our unit. Our material is aluminum 6061 T6. We're assuming a stress concentration factor of 1. Here's our fatigue exponent for that material, the fatigue strength coefficient. And this coefficient is valid as long as the stress is less than let's say about 90% of the ultimate, or maybe 85% of the ultimate. Duration. Now, duration is not going to affect the cumulative damage, but will affect the damage rate. So let's go ahead and calculate, and we come up with 2.1 to 22 e to the minus 13. So you can see down here we have that cumulative damage. There's also the damage rate. And at this point you should be saying, well, my goodness, the criteria for failure was damage equal to 1, or if you want to be conservative, the criteria for failure was 0.7, and we're so far below that limit that fatigue is just not a concern at all. And to that, I'm going to say, yes, that's true. Those are all true statements. So in this case, fatigue is just not going to happen. But let's go ahead and do a little bit more with this. We're going to play around and show you a few things. So here's how we calculate that bending stress at the fixed end for the beam. And this was the bending stress at the fixed end time history. And we did our miner's calculation. We did our rainflow and then our miner's calculation. And we came out, now the slide version number comes out a little bit different, but it's still within the same order of magnitude, so we're not going to worry about that. And I just want to go back for a second here. So I've got the miner's rule here. Actually, I think I need to go back in and insert a slide for the fatigue method, but okay. Anyways, moving on. So here was our damage results. So this is cantilever beam, fixed boundary, fatigue damage results for various input levels, 180-second duration, with a stress concentration factor equal to 1. So if we go with the spec nominal level of 6.1 GRMS with no added margin, the response stress standard deviation was 0.542 KSI, and the peak was about a 4 sigma peak, about on the order of 2 KSI. And here's the damage for the slide version, and we're not going to worry so much that our value that I just showed you in class was 2.1 e to the minus 13, whereas this was 1.78 e to the minus 13. And the reason is you have to remember any small differences in the response time histories are going to have huge differences in regards to the damage, because we have the fatigue exponent of 9.25. Just keep that in mind. And here we see as we go from one row to the next, we go up by a factor of 6 dB. So that doubles the GRMS value for the base input. Likewise doubles the response stress standard deviation value. And so these RMS values for the input and the KSI value, they're doubling with each step. But look what happens with the R value. It is not doubling. It goes up far more. And it's actually going up by 2 raised to the exponent of 9.25. Now if we go all the way up to an 18 dB margin, now our response stress is in KSI is 4.3. Our R value is 4 times e to the minus 5. And that is still so far below the limit of, let's say R is equal to 0.7, that we might be scratching our heads saying, why do we even bother to do that calculation? But let's do a little exercise here and see what would happen, or how long would it take to fail at the plus 18 dB level. So it's going to turn out to be 36 days. So if we take R is equal to 0.7, we divide by the damage to form a ratio. We multiply by 180 seconds, and then we divide by the number of seconds in a day. So, you know, the damage accumulation is linear with respect to time. So we can do this simple scaling. That comes out to 36 days, and someone had ought to fact check me on that, but hopefully I did that correct. So I come from a background mainly from launch vehicles, and so for launch vehicles, our components have to last for just a matter of minutes. But I know there's certainly other industries like the commercial aviation and automotive where different sorts of parts would have to be able to undergo vibration for maybe a couple thousand hours. But hopefully their input levels are nowhere near the ones I've shown here. Okay, let's talk about stress concentration factors a bit here, and here's just a diagram of an example where there's a hole in this bar, beam, or plate, or whatever you might call it. And there's different geometric parameters, the thickness T, width W, and then there's the radius of this hole. And depending on the ratio of the radius to the width, determines what the stress concentration factor is. So if we just have a little pinhole here, there is going to be a local stress concentration factor of 3. And I want to just emphasize that that's a highly localized effect that occurs. But the stress concentration factor would be as high as 3 based on this chart. And here's another chart. Okay, so here we have, so we've been talking about a cantilever beam. So imagine that cantilever beam is machined out of a big solid hunk of aluminum material. So there's different geometric parameters. There's a width, a radius of curvature. There's this H parameter. It's like the width of the actual beam portion here. Again, a thickness of T. So taking a look at all these parameters, we have a family of curves. And what this is showing me is that as that radius of curvature becomes smaller and smaller, So in other words, in the limit, as it goes to like a perpendicular corner, that these curves turn into hyperbolic type curves. But these are saying is that radius becomes smaller and smaller. The localized stress concentration factor could be as high as 3, or who knows, somewhere higher. So let's just assume, for example, that 3 is going to be the stress concentration factor for our cantilever beam. So what we could do, we've got a couple ways that we could apply that stress concentration factor of 3. Let me see if I can find where my Rainflow is. So we did the Rainflow, and then we went to the miner's cumulative damage. And at this point, we can say, okay, we haven't applied the concentration factor yet, so let's go ahead and apply it for our damage calculation. And when we do that, we get let's say 5.5 e⁻⁹. So kind of put that figure in the back of your mind. We're going to come back to it soon. First, I just want to talk briefly about just some kind of approaches here. In this case, we have a continuous beam. So if we want to know what the stress concentration factor should be, we have to look that up on a reference. But if we have a good finite element model with a fine mesh, the finite element model itself will hopefully lead us to what the stress concentration factor will be. In other words, the fine mesh model will, in essence, account for the factor. But a lot of times in vibrations, if we are going to do a finite element model, we use a coarse mesh model. And we don't like to spend the extra time and effort it takes to make the fine mesh FEA model. So we'll actually talk more about FEA models in future webinars. But anyways, for the case of the cantilever beam, we can do a spring mass model, kind of a lump parameter type model. Or today we're doing a continuous model. Or we can do a finite element model. And the finite element model actually can have a tie-in with the spring mass model. There's an analogy there that we'll get to in a future webinar. Okay, so let's, this data here, you've seen most of this data already, except a fourth column is added. And this is our cantilever beam, our fixed boundary, fatigue damage results for various input levels, 180 seconds duration. So the input levels for the 4 cases, the response level for the 4 cases. And here's the damage R for K is equal to 1. So these numbers you've seen before, and even when we get up to 48.4 GRMS, we still have so much margin to spare because our R value is, for our not to exceed limit, is R is equal to 0.7. But what about the case where we have a K is equal to 3? Now in this case, because this is a different example, the number turns out a little bit lower than the one I just showed you for our in-class exercise. But the fact that it's about 10% lower, let's not worry about that. So if we have a value of K is equal to 3, so that this damage does not go up by a factor of 3. Obviously it does not. Rather, for a stress concentration factor of 3, the damage goes up by 3 raised to the power of 9.25. So a significantly higher increase. So as you can see, if we account for the stress concentration factor, by the time we get up to 48.4 GRMS, the part will have failed. It will fail somewhere just below 48.4 GRMS. And that's again based on the 180 second duration. So we do need, one way or another, we do need to account for stress concentration factors. So that's kind of the point of that little exercise there. So please do not neglect those. We're going to switch gears a little bit. We're going to stick with that same beam example, only now we've got something new for today. We're going to do rainfall counting, and we're going to do it in the frequency domain. So rainfall counting can also be approximated via a direct calculation from a stress response PSD. And there's a whole number of methods that have been devised to do this. There's the narrowband, the alpha 0.75, the Benescuti method, Dirlich. Dirlich's very popular. Ortiz-Chen, Lutz-Larsen, also called the single moment method, Wersching-Light, and Sal Baker. And as it turns out, this Larsen here is the same person as Kurt Larsen, who is the director or the fellow for the NESC, Loads and Dynamics technical discipline teams, and he's the person I report to. And as a graduate student, he worked with his professor, Dr. Lutz, to come up with a method. And they like to call this method the single moment method, but I like to call it the Lutz-Larsen method in their honor. And we're not going to go over all the underlying formulas for these, but those are available in a paper on my blog. But in fact, and here's just the link to my blog at the bottom of the slide. And what these methods do is essentially they mix and match spectral moment terms. Now, we've talked about spectral moments before in previous webinar units. So the nth spectral moment, m sub n, for a PSD is equal to the integral from 0 to infinity. Then we have the frequency raised to the nth power. So n is whatever moment we want to assign. So that can be 0 or 1. It can even be a real number, so it could be 2.5, for example. Then we have our PSD, a one-sided PSD. We integrate with respect to frequency. Now, if we set n is equal to 0, then this first term just goes to 1, and this would be the mean square value for that PSD. Then we could take the square root. That would give us the overall RMS value. So this is our spectral moment equation. And the researchers that I mentioned in the previous slides have kind of in a semi-empirical sort of way used different combination of spectral moments along with Rayleigh distributions and other types of distributions to come up with these approximate methods for doing rainflow directly from stress response PSDs. And here's just another parameter that they would refer to. So if we take the fourth spectral moment divided by the second spectral moment, take the square root, that is equal to the expected peak rate, EP. And the 8 frequency domain methods, as I mentioned in the previous slides, mix and match these different spectral moments. And again, if you want to find out more information, please go to my blog, and you can just, whoops, what happened there? Just do a search on fatigue in the WordPress blog. Okay, so let's go back to our previous example for our cantilever beam. And we have an option to do a Psd input. So the first thing we're going to do, or the next thing, is to do a Psd input. And let's see if we can go and find where we need to go. Okay, let's go to this window here. I said window, it's really a dialog. So let's apply a Psd. And this is going to be okay, the input array must have 2 columns, frequency in hertz, and acceleration in g² per hertz. So in this case, we have our mill standard 1540B, that's our base input Psd. The response location from our left boundary is going to be 0, because we want to calculate the bending stress at that fixed boundary. Let's go ahead and calculate that. Okay, so here is our stress response Psd at x is equal to 0, corresponding to the fixed boundary. So we have our stress, psi² per hertz versus frequency in hertz. And most of the bending stress energy response is at the first mode, about 120 or so hertz. And then there's an additional portion of energy just below 800 hertz. but most of the bending stress is due to the fundamental mode. And then the overall level is 543 psi. So if we multiply by, let's say we expect a 4 or 4.5 sigma peak, then we get up to about 22 or 2300 psi for the peak level. Okay, the next thing we're going to do is save this. I'm going to save this as bending_stress. So this is going to be the response bending stress Psd. Save that into our Matlab workspace. Now let's go to our rainflow analysis. And this is actually going to be the rainflow analysis, but we're going to do it in the Psd frequency domain. So this script calculates the palm grid minor cumulative fatigue damage from a stress Psd via a number of methods. The input Psd must have two columns, frequency in hertz, and stress in unit square per hertz. In our case, we have psi. The stress array name is bending_stress. 180 seconds. And for now, we're just going to stick with stress concentration factor of 1. And you can go back and, as a homework exercise, apply a factor of 3 if you'd like. Aluminum is our material, so the fatigue exponent and fatigue strength coefficients are both library functions there. And then let's calculate. So this is going to be the fatigue damage from the rainflow cycles from the bending stress response Psd at the fixed end. So here's the stress Psd, and you've seen this one before. Now let's go to our command window. That's where we have to go next. And there's a number of esoteric parameters here that, if you really want to know what all these mean, you can go read the papers on my my vibration data blog. So if you want to figure out what an irregularity factor is or spectral width, but right now those are a little bit too esoteric for what we're doing. So here's our various cumulative damage values, and let's just focus in on this column of numbers here. We don't need to consider rate or the A times rate. We'll save those for another day. So here's all these various methods here, and they all agree, pretty nicely, but there is some variation. And as I thought about all these different semi-empirical methodologies here, these formulas, I thought to myself, I imagine there's a big glass container, and there's a number of jelly beans in that container. So you and your friends are each looking at that container, and you're each estimating what the number of jelly beans is. Well, rather than saying one person has the correct value, a smart thing might be to average several of those values together. And if you want, you can call that a meta statistic, I guess. So I thought to myself, rather than just kind of focusing on any one value, I'm just going to take an average of what I consider to be the 6 best of those methods. So here's my average of those 6 in terms of the cumulative damage. Well, let's go back to our slides here. So here's where we applied that Mill Standard 1540B Psd in order to calculate our stress response Psd. And then you've seen that plot before. That's the stress response Psd at the fixed end, so psi square per hertz versus frequency in hertz. And I have a note here. The overall level here is the same as that from the time domain analysis, which is a good sign. Then we went to our beam_bending_Psd, and okay, we had already done this, but now that we've done this calculation, we save that bending stress Psd, and then we go to the rainfall analysis. Okay, that's the purpose of this slide. And then we've already done this. We put in our bending stress Psd, our array name, duration, PSI units. We have aluminum material, and we put those numbers in. And actually, this is the older version 1.2. The newer version 1.3 has the option for the stress concentration factor. So I think I need to go and fix this slide, but you get the idea. And then we calculated what our damage is. Some of these statistics are esoteric, but otherwise we focus our attention on these damages values here. And this little format here is not quite the neat and tidy format it should be. The 1/2 actually should go over under damage rate. But here's our meta statistic here, the average of the 6 best methods. So if we take the average of the 6 best methods and we compare that to the result from our time history synthesis, again, this is both for a stress concentration factor of 1, and you can see that those values agree reasonably well. And the fact that there is some, whatever, 10 to 15%, whatever that difference turns out to be, we're not going to worry about that because, again, you have to remember, we're dealing with a fatigue exponent of 9.25. So any small differences get expanded very greatly by that fatigue exponent. So the time history synthesis method was kind of what I call the Rube Goldberg method. And if you don't know who Rube Goldberg is, please go do a Google search. So Rube Goldberg, that's his name. So if you're not familiar with Rube Goldberg already, again, please do a Google search. So the time history synthesis method was the Rube Goldberg approach. And the fast, direct, quick and easy method was the Psd method using the spectral moments. Well, so you might think to yourself, well, why not skip the time history synthesis altogether and just do the Psd method? And in some cases, that would be a good way to go. In this case, we already had our Psd. The Psd was understood to be a steady state, stationary Gaussian distribution type Psd. But what if, for example, we had a different situation where we had a time history from measured field data, and maybe it was a non-stationary time history, maybe it was a non-Gaussian time history. In that case, our Psd method is not going to work. So in that case, we have to just go ahead and do a time domain rainfall calculation anyway. So that's about all for today. So today, I guess two of the main things are we found out how we could apply this methodology to the case of a beam, where the beam is a continuous system where all the solutions are done based off the solutions to the partial differential equations. Then we also came up with a way, based on the efforts of the gentleman who came up with these methods, on how we could do a fatigue calculation in the frequency domain. So I hope you've enjoyed this webinar, and we have more fatigue and rainfall cycle type webinars in the coming weeks. So if you have any questions, please send me an email, and otherwise we'll see you next week. So thank you and goodbye.